Okay, question 4. This is a good one, isn't it? There's 3 separate parts, 3 entirely different topics. And they're all pretty big ones, actually. This is a tough question. So let's look at 4a first. Calculate the outer diameter of a hollow shaft needed to transmit a torque, magic word torque, of 40 kilonewton meters if the shear stress must not exceed 80 megapascals and the shaft has an outer diameter of 1.5 times the inner. So this is similar to before. Right. Looking at the formula sheet, we've got this torsion section, and it's almost identical to the general bending moment that we did, I think, in question 2. So it's nothing really to be too concerned about. It's the same type of question, just with different letters. So I'm going to, for convenience, take this formula section and put it on my sheet. So I'm going to follow my own advice here of when you see something a bit weird, or any time actually, just draw a diagram, state your variables, state your formula. You've already picked some marks up and it's helped you. So calculate the outer diameter of a hollow shaft. Got a hollow shaft here. And it's this kind of thing. Transmit a torque. T for torque, let's use the right letters. So T maximum torque is 80 megapascals, so 80 times 10 to the 6. If the shear stress tau, so that's interesting. So tau, curly T, is not to equal, is not, oh, check my reading comprehension there. Don't do that in the exam. Right, so torque is 40 kilonewton meters, 40,000 newton meters. The shear stress cannot exceed 80 times 10 to the 6. We've got a standard pipe type thing here, where J, this polar second moment of error, this is what we know as I usually, but when we're talking torque terms, we've got J. So J is equal to pi d to the 4 minus d to the 4 over 32 rather than 64. So that's interesting. Okay. The shaft has an outer diameter 1.5 times the inner diameter. So if this is little d, then this is 1.5 times that size. So let's start crunching this in the same way that we did question 2, I think it was. So we're going to have J is equal to pi times, right, remember we're replacing big D by this thing, so it's 1.5 to the 4 d to the 4 minus d to the 4. That's critical to remember to take that 1.5 to the 4, and I think I explained that in some detail in question 2. So look back at that question if you're not sure. I'll take a second just to crunch this, and let's see what we get. So we're going to have, and if I do 1.5 1.5 to the 4 is 5.06. So 5.0625 d to the 4 minus d to the 4 that's going to equal, well, I'll do it in separate steps so you can see what's going on, 32. So J is equal to, so 5 minus 1, so that's going to give us pi times 4.0625 d to the 4 all over 32. So I'm just going to crunch this section in the calculator here. So times it by pi divided by 32. That's going to give us an answer of J is equal to 0.398 d to the 4. Right, good. So we've already picked up a shed load of marks for doing that. And that's just a repeat of question 2. Okay. So it looks like, if you look at the letters we're working with here, we've got a T, we've been given it, we've got a tau, so it's these two sections, isn't it? They haven't talked about angle of twist, the length of the pipe, G, elastic properties, that's the equivalent of Young's modulus, I suppose. Right, so we're just using these two sections of the equation, so let's state it. So T over J is equal to tau, which is our limiting shear stress, over R. So then, let's plug some numbers in. T is 40,000. We haven't been given J. We've been given tau. And we haven't been given R, but we've been given something in terms of outer diameter is 1.5 little d, we've called that. So the radius of this cross section would be half of 1.5 d. So that'd be 0.75 d, little d. So we're going to get a 75 d. So we're going to end up with a value of J in terms of little d. Okay. To make this easier, I'm just going to take reciprocals. I'm going to flip both sides. So go over a minute. Think about doing this in your first week. And how far you've come equals 0.75 d all over 80 times 10 to the 6. So J is equal to 0.75 d over 80 times 10 to the 6 times 40,000. We're then going to be able to plug this into here, but let's just evaluate it first so that it looks a bit nicer. I'm going to pause the video because that's a beast to put in my phone. So I make that equal to 0.0000375 little d. We're now going to plug this into this. So we're going to say 0.00375 d equal to 0.398 d to the 4. So I'm going to divide through by d. So that'll become to the 3. I'm then going to divide through by 0.0398. So that's going to give me 0.00375 over 0.398 equals d. D cubed, So if I were to cube root both sides, that's going to give me D. Right, second to calculate that. So that equals, by my reckoning, 0.098. That's a solution for little d. Therefore, big D equals 1.5 little d, according to the question, which is equal to 0.147 meters times it by 1,000 to get it in mil, which is equal to 147.05 millimeters. Oh, I'm nervous now. Yes, 147 and 98 mil. I like it. So it's exactly the same as the first question, really, or the second question. You just use different letters. It looks like this is a key technique they want you to use. So we'll cover this in a revision session. In the meantime, work this through. Have your own notes, because if this comes up, your own notes and having practiced it will definitely stand you in good stead, even if it just means you start doing it by rote learning to begin with until you start seeing the patterns and the logic behind it. Good. I'm going to do parts B and C in a separate video.